So let's look at a particular example of Newton's application of Newton number 2, where we have, let's say, we have a mass m on a frictionless surface, and it is being acted on by a force F. Because here's my mass m, and here's the force F. Let's say the force is the F of a spring pulling so that a constant force shows on the spring, or even better, a spring scale. And so this is the force of the spring on the mass m. And so there's no friction, something I haven't mentioned yet, but we'll definitely be talking more about friction. And so if I did a force diagram for M, here's what it would look like. So there's horizontal forces and vertical forces. So let's do the vertical forces first. There's going to be some downward force, force of the Earth on mass m, and that's just going to be equal to mg. And if this is, let's say, a table right here, this dotted line, so let's say that's a table, then there's going to be an upward force, which is going to be the normal force of the table on little m. These are going to be equal and opposite to each other. We can tell they're equal and opposite because m isn't accelerating in the vertical direction, and so the forces in the vertical direction add to 0. And so I can say that here. I can say F net y on m, I'll give another m there, is equal to 0 newtons. Okay, now in the y direction, we have no friction, and so we have one force and only one force in the x direction, which is going to be this F of s on m. So from the fact that the net force in the y direction is 0, we know that a y is equal to 0 meters per second per second. But for the acceleration in the x direction, so let me draw a coordinate axis here, because again we have the same bookkeeping issue that we did in kinematics, x and y. And so I've got the force in the horizontal direction is pointing in the positive direction of my x-axis. So a sub x is going to be equal to the force of the spring on m divided by m. So let's put some numbers in here so we can actually see what happens. I'll just change color. So let's say in this particular example that m was equal to 100 grams. I'm using gm instead of just g to distinguish grams from the acceleration of gravity. And let's say this force was equal to 5 newtons. And so you'd have to, if you were doing this experiment, you'd have to continue pulling this spring scale here so that it always registered 5 newtons. Okay, so in that case, if we plug these numbers in, these particular numbers, I would have the acceleration in the x direction would be 5 newtons, and I bookkeep this 5 newtons as a positive force because it's pointing in the positive x direction. Bookkeeping rules same as for kinematics. And then the mass is now 100 grams. But again, safe thing to do is to always convert mass to kilograms. And so we're going to do that here. 100 grams is 0.1 kgs. And so that would give us a acceleration of 50 meters per second per second. That's a pretty large acceleration. So we have um, roughly 5 times the acceleration of gravity. And you should have some appreciation for what the acceleration of gravity is just from real life. And so this is 5 times as big as that. You can also see from this equation how you get big accelerations. And so either you make the numerator big, that would be the force, or you make the denominator small, that would be the mass, or you do both. On the other hand, if you have this same force acting on a 1,000 kilogram mass, the acceleration is going to be much smaller. And so acceleration is inversely proportional to mass. It's directly proportional to force. These are simple but important ideas.